Hi all, welcome back to Theoretically Podcasting. I'm Vasu Sham, and I'm joined today by my friend and collaborator, Michael Buchhold. Hi, Michael.
Hey Vasu, hey guys, nice to meet you.
So Michael's currently a postdoctoral researcher in Cologne. So could you tell us what you're mostly interested in and what your trajectory has been?
Yeah, right. I don't know. I since I started my PhD, which is 10 years ago now, it's a long time. I'm interested in non-equilibrium physics and more or less kind of really non-equilibrium quantum many-body phenomena. And there I came from the background of cold atoms, more or less, where I say cold atoms was the place to be if you were interested in driven systems, kind of open systems, where I say so you are manipulating many body systems that are quantum mechanical, so of bosons, spins, or fermions, with some external drive, maybe some laser, or maybe some time dependent magnetic fields, and you have dissipation, for instance, coming. You have particle loss, so your particles are dropping out into the environment, or you have some coupling to a cavity where you have photon modes around, and so this is kind of inherently kind of driven open quantum many body systems, and they're looking for novel kind of types of quantum phases. But in particular, I'm interested in universal phenomena. So in particular, since then, I'm always looking at kind of can we identify new situations of quantum phase transitions out of equilibrium, or quantum
I see.
critical behavior out of equilibrium. So that's what I'm interested in. And then I've moved around, and what is nice kind of is that now more and more kind of different, I say, communities realize that open systems are actually extremely interesting. So when you talk about condensed matter, there is this whole business of ultra fast driven matter, where people are kind of driving material very strongly, and then you realize, well, if you want to describe the relaxation of a material far away from its equilibrium state, then you need to take into account that these are open systems, because you're mainly interested in electrons, but electrons talk to phonons, for instance, and phonons, they're typically is a continuum that absorbs energy or momentum or whatever. And so solid state materials now are kind of considered also as open systems if you do the right thing with them. And you have in quantum information theory, you have all these decoherence channels, that's open systems. And so I think there's just a large variety of different systems. And
Yes.
of course, what we are going to talk about today is systems that are measured, and the measurement apparatus is also something that makes the system open, because you act on the system from the outside.
Right. Well, I mean, I guess what you're emphasizing is that there actually aren't any truly closed systems because
Yeah,
ultimately,
so one can see it that way. It often makes sense, right? So very often you can see you can look for some ground state or some thermal state, and then if you have a coupling to a continuum of an environment, you say maybe this coupling is irrelevant in some sense. Most often it's irrelevant in some randomization group sense, where I say these couplings are very weak, they don't change the ground state. As the kind of the Born-Oppenheimer approximation more or less says, yeah, well, they don't really change the ground state or the thermal state much, or they are really irrelevant in the RG sense. That means on the longest distances, they don't change the nature of the state of your system. But if you think about relaxation, then that's a different story. Yeah. So the
right.
simplest thing is take a Luttinger liquid model, some quadratic fermion model, and say, okay, the cubic terms like dx phi to the cube, something like this. This is RG irrelevant. It doesn't change the physics of the ground state, but this is the term that lets the system thermalize if you evolve it in a non-equilibrium state. And time now is important, because if you wait for a long time, RG irrelevant or irrelevant couplings can become relevant in the sense that they tell you to which kind of final state you are relaxing.
Right.
There this openness suddenly becomes much more important.
Yeah, this is I guess this is something that some people might call dangerous irrelevance. And indeed, there are contexts even in high energy physics where people have looked into this. And a lot of them are cosmological because clearly in cosmology, there's a sense in which you are dealing with an open system. And I mean, it manifests itself in different ways, but one of the ways is just what the light scalars experience in an expanding universe like ours. If you take inflation seriously, there's this model of so-called stochastic inflation that
Mm,
basically accounts for the effect of all these long wavelength modes re-entering our horizon, had them being frozen. So there's a reservoir of these frozen modes which after the universe starts to expand in accordance with non-inflationary dynamics, they start to re-enter our,
yeah,
the horizon and give rise to some very interesting stochastic dynamics. But it's important to realize that they came, their effect is not irrelevant for the question of what's happening in those very long distances. And
yeah,
much like what you described, okay, we can use regular, in some sense, quantum field theory within the observer patch, deep within. You could even pretend like you didn't know that the universe is expanding, but when you
yeah,
get to the radius of the extent to which we can see that there's the observable universe, then all of a sudden these things start to matter. So it's yeah, I think that overall it's like a very important topic, and the only reason that more was not done prior to contemporary times is probably just because it was just too hard. Or it's probably still too hard.
maybe it's too hard, but I also have the feeling that the questions are really changing a lot. So kind of
Mhm.
in particular, as I said, I'm working on this since 10 years more or less, the same topic. I mean, it's different systems, but it's always so when you have openness, when you have dissipative terms. And in the beginning, there was like from the solid state community, there were mostly the comments like, yeah, this is some cold atom stuff. This is not interesting for
Mhm.
us. And now this becomes kind of now those guys are coming to us and say, look, I think we have some open system dynamics here. I said,
Mhm.
yeah, I mean, of course, but also
Right.
because it was just not needed before. It was just not necessary to include it, and therefore it was not appreciated. And what you just said reminds me when I was at Caltech for 3 years as a postdoc, and there was actually already a lot of interest from people from high energy physics. So this is kind of, since I'm coming from a very different area,
Mhm.
so I just call everything high energy physics. I hope nobody kind of now is offended. Where they said like, so we have these problems like evaporating black holes, like the expanding universe. So those things, we should consider this as open systems. But I think there's also there was essentially a language barrier where I was just not understanding what we were talking about. And I
Mhm.
think the same happened from the other side. When I was talking about some dissipation channels, like, what is this? I don't know.
Yeah.
So
Right.
things are evolving, and maybe we're getting connected better.
Right, right, right. No, and I think it's rather interesting because I mean in the large sort of scale picture of things, you can say that in principle there are no actually isolated systems, except if you thought about the universe as a whole. And
Yeah.
there
And that's again the question: is the universe now a pure state, or is it mixed, or I mean, is it actually totally isolated? I don't know. Like this is
right,
maybe
right.
we'll never figure out, I guess.
Maybe, but I think that that's sort of a it's sort of one of those things where you go there and back again, where in some sense you can take very like isolated systems as being like idealizations of systems in a laboratory. And
Mm,
then you say, well, not really though. I mean, for certain questions, yes, but for a lot of other questions, no. And then
right.
you're in this intermediate scale, which is quite realistic, and it maybe describes in some or the other sense most of the things we deal with, right?
Yeah.
Especially if we're talking about, collective behaviors of, many body systems where, as you
Yeah.
mentioned, like the electrons can't ignore the phonons, or, like a system like, I don't know, quantum computer cannot really ignore its environment and it
No,
is
no, no. Of
decoherence.
course.
But then, okay, you can kind of zoom out all the way, and then you have to ponder, like, well, there's only really one thing that we can kind of call a closed system, if anything, and that's probably the entire universe. And yeah, so some of us kind of are puzzled about that, but I think that it's, yeah, we can table that discussion um in favor of what we're going to talk about today. So the fact that you mentioned these phase transitions induced by the system essentially being open, as in you have these seemingly irrelevant operators for the purpose of describing, say, ground states and so on, that play a key role when it comes to phenomena like relaxation. But also that they can, that there's some interesting and novel phases that can come about because the system is, very beholden now to what these kinds of, and environment in the generalized sense related effects do, and that they can give rise to now some novel kinds of phases, or some novel sorts of quantum phases. And what I'm curious about here is whether the terminology we would use in the conventional sense of talking about different kinds of orders, right? Is applicable in this context. I mean, are these just more kinds of order that manifest, or is the paradigm? I mean, everybody says that, oh well, you need to abandon the Landau paradigm for regular classical phase transitions in favor of the more quantum mechanical ones. And then now people are saying, well, no, not really, because all those are just like these one form and generalized symmetries. And so it's still the Landau paradigm for those kinds of generalized symmetries. But here you have something even different happening. And at least in the example we'll look at, it'll be clear that, well, you don't even strictly have unitary dynamics, so the kinds of models are sort of somewhat different. And I'm curious if you anticipate that if these are like really some new sort of truly beyond Landau orders, or if there's just more of the same story in a different form now. Like what happened with the one form symmetries, higher form symmetries, and so on.
So this is a very interesting question. I mean, and this is something we are trying to figure out also since a long time. So since a long time, I'm working with my PhD advisor, Sebastian Diehl, and this is a crucial question. And of course, you have in equilibrium, you have a very nice kind of structured theory building where you say you have symmetry breaking. Symmetry breaking is associated to kind of forming an order parameter that is non-zero. And then you can say, okay, and now you have your universality classes, which depend on essentially on the type of symmetries that are broken, and maybe the number of relevant operators or the type of relevant operators that you have at the critical point, more or less. And this all works out, and that's the beauty of equilibrium. And now there is maybe different perspectives. If you move away, then a question that we often get is like, once we move away, then everything is unclear. That's what people often ask. So if we move away from equilibrium, are there any of these paradigms kind of surviving? Is everything immediately lost, or how do we think about that? And I think kind of, again, like equilibrium is very constrained in many ways. If you look in quantum mechanics, your lectures, you have, for instance, also you have something like this Kubo-Martin-Schwinger type relations that tell you exactly how correlation functions have to be, or the boundary conditions of imaginary time Green's functions and so on. These are extremely constrained, and so kind of equilibrium seems to be the point where a lot of different laws come together. But of course, out of equilibrium, you can still talk about symmetry breaking. I mean, you can have symmetries out of equilibrium, and you can break them. And you can have order parameters out of equilibrium where you say, well, I have a transition where in a whole range of parameter space, I have a zero order parameter. And in another parameter space or region, I have finite order parameter. And in between, there's a transition separating these two. But what one has to say, there are also examples where, for instance, you have phase transitions between two phases where you cannot really identify a broken symmetry between the two.
Right.
Maybe there is none. Maybe people have not identified this, but there are examples. So there are examples of, for instance, absorbing state phase transitions is a term. that describes, for instance, situations where you have population dynamics or epidemics, where you have a transition from a phase where you have no order parameter, which means, for instance, you have diseases that are not spreading. And on the other side, you have an endemic phase where disease is spreading, and there's a critical point in between where you see everything that you're used to from critical phenomena. You see algebraic behavior, you see the absence of scales, and so on. But there is no symmetry that is apparently broken in the two phases. Yeah? So, and that can happen. Or you also have phase transitions without order parameters, for instance. So, but you can still understand what's going on there, and maybe you have to be a little bit more flexible in some sense.
Right. No, that's very fascinating. I mean, all these behaviors are extremely fascinating, especially because they push these paradigms beyond necessarily just the statistics of physical systems of many bodies, right? In principle, there's there's notions of phases and phase boundaries and so on for things that are more general than just what we would normally think of as statistical systems or whatever. And
I mean,
yeah,
these concepts in equilibrium are super powerful.
right.
That's why we are used to them.
Right.
And why we love to study them, because we love to categorize things, and we love to kind of give certain patterns and then distinguish them. But yeah, so I mean, things can be more diverse probably in out of equilibrium. This doesn't mean that it has to be different. Maybe these things just have not been well identified.
Right.
So what kind of symmetries? Maybe it's a different one where you have to incorporate. There are also examples where I say, well, if I just look at the static part, I can't identify a symmetry. But if I incorporate like the time evolution of the system there on this level, I can suddenly identify a symmetry that is just not a conventional one, where I say maybe something you have a phase where something like ergodicity is broken,
Yes.
and the phase where ergodicity is restored. And this you can express in terms of a symmetry if you are clever enough. But it's not a conventional one where you say, now I have Goldstone modes or whatever. Yeah, so it's not so easy. Yeah.
Right. No, that's always, again, for high energy physicists, if you have a puzzle where you seem to have behavior where there's a symmetry breaking, but there aren't Goldstone modes, then you're tempted to try to think about these as not necessarily bosonic symmetries, and so that that's yeah. So anyway, but what we'll do today is go through paper here about a very specific kind of how should I put it, like non-equilibrium behavior having to do with measurement, but not just right. So well, okay, it really covers the range of what we might consider conventional measurements from the postulates of quantum mechanics all the way to weak measurements in the sort of spirit of what people like Aharonov would tell you to think about or to ponder. So this I thought is very nice because it's this. So here's a paper that one of the papers you've written about this. You have more than just this work about this, and as far as I understand, this is sort of close to the heart of your main research interests right now, like as of now. Is that right?
That's right. Yeah.
Yeah. So yeah, could you sort of walk us through this idea? I mean, I find it quite fascinating that there are these measurement-induced phase transitions. So
yeah,
what are the phases here? Like just broadly before we go into details.
what are the phases? So maybe, I mean, yes, this paper is about a fermion system, and because we wanted to have some field theory at the end, we used Dirac fermions in the continuum. But I think that's not necessary to understand the general concept. And the general concept, that is that there are many papers of this measurement-induced phase transition, or a lot of attention they have gathered in the last 2 or 3 years. And the basic idea is this. So you say, let's take some system of, I don't know, spins or bosons or fermions. So you have some quantum mechanical degrees of freedom. And if you just take them and you apply something like local unitaries. Now, local unitaries can be many things. It can be really kind of gates that connect two different degrees of freedom, so unitary gates. But it can also say you take a local Hamiltonian and you do a time evolution with a local Hamiltonian. So if you are in some eigenstate of an Hamiltonian, so let's use the language of Hamiltonians. If you are in an eigenstate of a Hamiltonian, not much is happening. Of course, you just get a phase during the time of the state is not changing over time. But if I'm starting with a Hamiltonian that has as eigenstates, maybe that is translational invariant, and I start with some initial state that is a product state, a local product state, and then I evolve this over time, then this product state is typically not an eigenstate of the Hamiltonian. It's actually a superposition of many different eigenstates. And so what happens is that this Hamiltonian now starts to kind of scramble local information or to build up entanglement between different sites. The product state evolves into an entangled state. So now you can see this from many different perspectives. There's maybe thermalization going on in the system, kind of coming from the Hamiltonian eigenstate thermalization hypothesis and so on. Or you can say, really, if I'm looking at the entanglement, what happens is entanglement is kind of spreading. If I'm measuring entanglement between different regions, I see a type of light cone where entanglement is spreading between these regions, and these become strongly entangled. This just means, in the language of quantum information, this means there are now many qubits in this system that are extended over a large region in space. So if you start in a product state, this means you're having local qubits. Now you do this evolution. Now what you're producing is qubits that are extended over space. And if you make a cut in your system and measure kind of how are they correlated, you see very strong entanglement because all of the qubits are now non-local.
Right. And this is basically seeing the entanglement entropy as the number of like Bell pairs you can sort of distill from this
system. Yes. So you can see it as the number of Bell pairs, or in general, for a more complicated system, it's really the number of correlated quantum states in some sense that you have. And this becomes large. Of course, it has an upper bound depending on the system size, but it becomes really large. But now what you can say is, okay, what happens if I'm making local measurements? Not at the end of this evolution, but during the evolution. But when I measure, for instance, I just measure the occupation of a site or the orientation of a spin. If I do that, I get an answer, I get plus or minus, and I get a projection of this local spin onto this measurement outcome. But this also means that I'm taking this local spin out of this correlate many-body state and putting it in back as a product. So if I measure a single spin, what happens? I take out the spin, I get an answer, and I now have a product of the whole entangled state without the spin times this local spin. So this measurement, of course, reduces entanglement now because this thing is entangled with nothing after the measurement.
Right.
So and it is clear if I do this Hamiltonian evolution, I get this totally entangled state. I measure all the spins, then I just am in the product state. It's boring. So, I could have saved the whole kind of unitary evolution because I'm back in my initial state. But I can ask, well, if I now have a certain rate with which I'm doing these measurements everywhere in space, so where I'm taking out local spins, can I still get an entangled state? Can I still get kind of a large number of extended qubits, or does this ruin this kind of situation? And this is actually so one of the first papers that came out of this direction was by Matthew Fisher and his PhD. He's a professor in Santa Barbara, and he told us when we asked him that his idea was to ask, so if we are now thinking, if we are going beyond, let's say, chemical reactions where quantum mechanics plays a role, can actually quantum mechanics play a role in living beings? Because what quantum mechanics means, we are entangling things, right? Or we have coherent superpositions, but at the end, we are asking, can entanglement survive over larger distances, over larger times? And so what we
Indeed.
can imagine is that, I don't know, in our body or in organisms, we can have unitary gates somehow that entangle local degrees of freedom, whatever they are, they're molecules or whatever. But they are now also subject to measurements or decoherence. So will
Right.
this destroy all quantum entanglement, or will some entanglement survive? So is everything that goes beyond, to break it down, make it a little bit too simple, is everything that we see in nature super classical and quantum mechanics stops at the level of chemical reactions? Or is there quantum mechanics involved somewhat on bigger scales,
Yes.
larger time scales? So
Right, right. Well, I mean, this is very fascinating because I mean, I hadn't appreciated this motivation, but it was a question that essentially came up when I was thinking about this. And just prior to recording, I was asking you about how you can think of perhaps the environment as playing a role of some monitored weak measurement system. Because I guess
yeah,
one thing that you didn't mention is that in order to have something in between these two possibilities, where either have unitary evolution entangling everything, and you as an experimenter are just asleep, or you sort
yeah,
of wake up and decide, oh, wait, no, I gotta measure this now. And then,
yeah,
right, having made a measurement, what you've done is you've discovered what was happening. As in, you can infer from, say, if you manage to measure all the qubits, you can infer, like, just draw like CHSH tables, if you're literally thinking about these as qubits between the various
yeah.
constituents, and find that there are all these correlations. But in so doing, you're back to square one as far as the evolution was concerned, right? Because there's this
Yeah,
interaction with the system that just projected it
yeah,
to given eigenstates of, say, the Hamiltonian. Or you could do something a little bit weaker and not collapse the state entirely, but as a result, not be able to recover complete information about the state of the system either, right?
yeah.
But what this allows is a possibility that you don't entirely derail the unitary evolution of the system, that it's
Right.
still doing whatever it's doing. You've just kind of sort of distracted it a little bit. And now the way we talk about classicality is always in an extreme view, which is kind of like what we, the first option. It's we treat the environment as if it's a thing that does the first, right? This is it's a measurement that just takes everything, right? And then
Yeah, yeah,
sets it all back, and then it's doing this somewhat continuously. So in essence, you're only left with this effective nonlinear evolution that you can track of observables, which we call classical mechanics. And
mm,
you need things that happen fast enough for the environment not to be able to catch up with it.
yeah,
If we're talking about terrestrial processes, so maybe there's like some reactions and so on, and that's like what you mentioned here. Whereas the things happening on the other time scales in biology, maybe they're just all like, yeah, there's just not enough room for the entanglement to spread really, right, across the scale hierarchy, just
yeah, yeah,
because there's just measurements all the time. But and there's the same thing you say, or what people say when they try to motivate their study of novel quantum phases. They say, oh, you see, like what happens is that if you have a small system, then we can have these entanglement things and so on. But you can't actually have Schrodinger's cat because the decoherence will make it such that the cat
yeah,
is just classical. So then what we're going to say is, well, let's ask about actually building these cat states. And are there like these strongly correlated enough systems where you can sort of
yeah,
have a piece of material in the lab which actually is behaving for all practical purposes like Schrodinger's cat, for lack of a better, a better
yeah, yeah.
analogy. Uh, but in fact, it's unclear that the cat is actually
Right.
entirely classical either, right? So, and that I think, okay, no, that I think is very fascinating. And yeah, okay, no, so this is very good. And so what you have here is a simple enough system where you can indeed model this spectrum of possibilities between
Yeah,
being able to just make a strong measurement versus something that's so weak that you've almost done nothing, right? So
Yeah.
that's kind of the setup. So
Right.
maybe we should look at first the sort of more discrete setup, and then we can kind of jump to what's going on. Well, let's see. Let's see if we can get to the basic setup here. Okay, so
Right. So
here's the
maybe
sort
I
of
just
yeah. Go on.
I start with the general setup. So there have been now, just to finish maybe this thought, there have been now what people have discovered. If we're just using random unitaries, like drawing from a hair random ensemble, drawing unitary gates, then what happens if we don't measure, we get this super strongly entangled state, which has a volume law entanglement in one dimension. So I'm always talking about one dimension that has a volume law entanglement. And now I start to measure, and just measuring with a small frequency during the unitary gates, my state remains super entangled. So I have still a volume law entangled state. So many of these non-local qubits remain preserved.
Okay.
Again, keep in mind, I'm breaking down everything in the most simple case. So we
Sure.
cannot think of individual qubits more or less, but kind of they are, that's a good picture. But then suddenly, if I go across a critical measurement strength,
Okay.
then all these kind of the unitaries are not strong enough to build up entanglement, and the system collapses into an area law entangled state.
I
And
see.
so this is the type of transition that people saw, is that when you measure too strong, no entanglement is built up. But if you measure weak enough, then you build up a volume law entangled state, and there is actually a sharp transition between the two, with all kind of features of a critical point, namely that you have a logarithmic growth of the entanglement entropy with the system size, and you can identify type of order parameters. Now, these are complicated, so we will get to that. Those are not the regular type of order parameters that one would expect, but there is this transition. And what we were thinking is, okay, I mean, how random unitaries and projective measurements of qubits, that's like a tough story to do some analytical or to get some analytical understanding. So some people really love the hard random unitaries. I don't understand this stuff. Yeah? So this is kind of, I need something simpler. And so we thought, can't we find a more simple model, like maybe the most simple one, which displays such a transition in the entanglement entropy or in the behavior of entanglement when we measure this system. And so we came up really, as I said, maybe with the simplest case. We weren't the first one to look at this, I have to say, but somehow the interesting part was missed in the previous paper, and so we were lucky. So we looked at this again, and we found kind of, if we're just looking at a lattice, one-dimensional lattice, on which we're having fermions, non-interacting, just free fermions, and we have a Hamiltonian where the fermions are hopping between different sites.
Right.
This is Hamiltonian, exactly. And then we're doing measurements of the fermion number on local lattice sites. So we're measuring kind of whether there is a fermion or not. This is kind of a 1 or 0 answer. And so you see, if you measure a lot, if you measure like much faster than the Hamiltonian does anything, you will just know on each lattice site, there is a fermion, there's no fermion, and you know where all the fermions are, and the Hamiltonian can't change that, because you have a quantum Zeno effect, you're just measuring constantly. But what was fascinating was when we have this Hamiltonian being stronger or measuring with a smaller frequency, then we find actually that the fermions are non-localized, and they form a state with the logarithmic growth of the entanglement entropy, which you associate typically to a critical state, like a ground state of a Luttinger liquid theory in one dimension. And this was super surprising. So we did numerics, we tried to identify this, and yeah, we saw this, and now we wanted to kind of look at, can we analytically understand what's going on in this system? And that's what we're discussing in the paper. And there's one thing that we should mention. We're not looking at projective measurements here, but we're looking at something that is called a continuous weak measurement.
Okay.
And the continuous weak measurement is, if you kind of, it has the same properties as a projective measurement. If you measure long enough, you know the full information on the state, but what is actually happening, you're trying to continuously measure some auxiliary system and try to gain information about this. And the simplest type of weak measurement we all know, actually, it's the Stern-Gerlach experiment, where I say what you want to know is the spin of an atom, but you don't know how to do that. So what you're doing is you have a gradient magnetic field. And so this gradient magnetic field gives you a coupling between the spin and the position of the atom in the z direction. And now what you can imagine is you are sending this a spin through this gradient magnetic field, and then you're constantly looking, how does the position of the spin change? Does it go up or does it go down? And there is, of course, a lot of uncertainty, because just measuring the spin a little bit more up than it was before doesn't mean immediately that it points upwards. It just gives a higher probability that it's pointing upwards.
Correct. Yes.
So what happens if you trace long enough where this spin is going, eventually you will see it's going up, then you are sure it's the upspin, or eventually it will go really down, then you know it's downspin. But if you just measure constantly, you will just see it more or less has a tendency towards one of the two. And that's what we're implementing here.
Right.
And the scale on which this happens is gamma in this equation 8. And gamma is really the scale. So gamma is a rate, and 1 over gamma is the scale, the time scale on which you would have to measure this in order to be sure whether you are up or down, or in the Fermion language, whether you have a particle or no particle.
Yes.
On a time scale 1 over gamma, this is the same as a projective measurement. You are sure about the outcome, but on a time scale shorter, you are not so sure. Can be both.
Right. No, thank you for that. But could you sort of, okay, so you set up the problem. Oh, here's the local measured operator, which is, for instance, the local density or something.
Would just be the Fermion number operator.
Right, the Fermion number. Exactly. H is the free Hamiltonian. And here you have this equation that tells you how the state evolves. And it's not just a Schrödinger equation, clearly, right?
Yeah.
Which would have just involved this term. But it involves, since you have this measurement protocol, it involves these two terms. And you call this a diffusion process. So you break that down just to, is it a choice that you make in the scheme that makes it such that the evolution has this format, or is there something deeper going on?
So when you think about continuous measurements, you can have different realizations of this weak measurement process, for instance. So and which one you pick determines how your stochastic Schrödinger equation evolves. So it's stochastic,
I see,
because measurement outcomes are stochastic.
Right.
And it's still on the level of a Schrödinger equation. It's a pure state, because measurements don't change the purity of they can purify a state, but if you start with a pure state, you'll remain in a pure state, right?
Yes.
And so now you have a continuous evolution, because we assume we are continuously monitoring the system. And how do we do that? As I said, imagine now we have each local lattice site of a fermion, we couple to some position operator.
Okay.
And say, okay, now what we are doing is we have a coupling of the local density of the fermion to some position operator of some other degree of freedom. It's called a meter very often in this kind of quantum optics or quantum information framework. And now this X, this position degree of freedom, has another conjugate momentum, because each position has a conjugate momentum. And so we know kind of if n is 0, if the particle number is 0 in our state, then the coupling to X is 0, and P doesn't change over time. P is then conserved, because the total Hamiltonian is X times n. If n turns out to be 0 on this state, then there is no coupling of the Hamiltonian to X, and P is conserved over time.
Right.
On the other hand, if there's a particle, then we have a coupling, then we just have X effectively for the meter, and so P will evolve over time. And so
Right.
what I'm measuring then after some time is what is the value of P?
Yes. Yes, I see.
And when P has changed, I say I have a probability that the particle is there. If P hasn't changed, there's no particle. But of course, because it's quantum mechanics, I have uncertainty in the measurement of P.
Right.
And this uncertainty translates into what we have in equation 8 is this dW is a Wiener increment. This tells you when I have a readout, I still have uncertainty about where the state is. And now, of course,
Very
the
cool.
math is complicated walking through this, but this is where it comes from. So this is where it comes from.
Very interesting. No, that is a yeah, that picture does indeed make sense. And now basically the readouts of P are in the analogy to the Stein-Gerlach experiment, like whether you're deflecting upwards or downwards, and at what rate. I see.
Yeah.
No, that's somewhat clear. Now, but to just take this back to the language of diffusion, it looks here that like you have a diffusion process where these two terms, well, let me see if I am getting this right. So if I neglect the Hamiltonian for the time being, then it looks
so
like
for this diffusion, you can neglect the Hamiltonian.
Right. Because it's essentially driven, I mean, yeah, well, the measurement is sort of at the heart of the stochastic nature of this process, not the deterministic evolution. But if I just do that, then it looks to me like the variance of the distribution of these outcomes is set somehow by gamma, or that gamma plays a role in the variance of this, just from thinking about this as something like a Fokker-Planck equation, or like something of that nature. So this presumably comes from the sort of variance part of this dW.
So we can look at equations, so we can break down this more and look if we take equation 9. So this expectation value is in the current state. So we take it in the current state. And let's take for the moment maybe a spin instead of a fermion, because that's simpler. So a spin can be +1 or -1. And now this expectation value is somewhere in between, because I'm not necessarily in an eigenstate of a spin. But let's say I'm in an eigenstate where this is not 1, but it's 0.9. So I have a very strong polarization towards spin up and just a very tiny admixture towards spin down. This I already know if I look at this expectation value, but I'm not yet in an eigenstate of this spin. So it could still be that during this weak measurement process, I'm going in the other direction.
Yes.
The first term tells me that there's a tendency to minimize this variance. Namely, it tells me if I already have a large probability to measure spin up, then in the next time step, I will deterministically move closer to actually the spin up state. So this is really the deterministic part of this continuous measuring, as if I had a classical particle that I'm observing. Where I say my X and P, my meter, is not a quantum system, it's a classical system. And then I know if I have this situation that I'm measuring the particle and it's already in 90% in this spin-up state, then in the next time step of this continuous measurement, it will just go closer to this.
Yes.
So it will approach. But then you have the stochastic part, which tells you maybe you're all wrong. Maybe this readout told you that your expectation value looks like you have 90%, but actually you measured this meter far out on the Gaussian kind of spectrum, and so you are wrong. And with a kind of very unlikely process, it can kick you back towards kind of the spin down scenario. And so you have this kind of deterministic part, which tells you if you are already very likely in one state, you will get closer to that state deterministically by making this continuous measurement. But there is a scenario where you actually kicked in the other way. And so if you imagine this spin now being on the Bloch sphere, between up and down, then what this does is it gives you diffusion on the Bloch sphere. So if you are in the North Pole or the South Pole, they are absorbing, because if you have a definite answer, you will not change anymore if you are in an eigenstate. But if you are somewhere here, you are still kind of diffusing around. It's the diffusion is the strongest around the equator. And then you have kind of a bias diffusion where you go closer to one of the two, either the north or the south pole.
Okay, I see. No, that's very instructive. Great. So this is a sort of cumulative evolution of this state, accounting for both the measurement process and for the actual quantum evolution.
Yeah.
And now we have a sense for what this evolution is doing exactly. Great. So here you sort of break it down, right? So that I guess you even spell out some of what you just explained, that you have a deterministic contribution.
Yeah, this might be. So you have this deterministic part essentially, which gives you the Hamiltonian and is pushing towards the most likely eigenstate. And then you have the kind of stochastic part of the measurement.
Right. Okay. No, very interesting. And indeed, the noise here, it has a variance that knows about the gamma.
Yeah.
Very cool. Now, yeah, so you can, okay, so you sort of explain how you extend this beyond the state to the density matrix. And it roughly does what one would expect. But you now mention, okay, so clearly there's some limit where you can talk about just projective measurements, right? And this is when what you just first explained about whether you're measuring, whether the dynamics, so there's some competition between the dynamics set by the Hamiltonian and then the timescale set by gamma. And if you just, so I guess, could you explain how it manifests at the level of this?
So in principle, if you like, so for me, going to continuous measurements is a formality that allows us to take a soft continuum limit.
Okay.
To say what happens now is we have a well-defined way how to express a measurement in a continuous time.
Okay.
Because if we're thinking we can do that with Hamiltonians, of course, Hamiltonian evolution is continuous in time. That's fine. We can write down a field theory for any kind of analysis of critical phenomena. We would like to write down some continuum field theory. Well, you don't have to, right? So, but this is kind of how I imagine kind of critical phenomena. I want to have some continuum action, and I want to analyze this using RG, kind of really Wilson type RG in momentum space. And that is how I understand critical phenomena. And the continuous measurement gives you a framework to formulate a measurement continuous in time. And there is the time scale or the rate gamma, where I say, if I'm looking at shorter times at this measurement process, times that are shorter than 1 over gamma, I see a difference between a continuous measurement and a projective measurement. But if I'm looking at time scales larger than this gamma, then there is no difference. And this is kind of essentially right. This is exactly in this notion of universality or RG, irrelevance and relevance, where I say I have this different microscopic descriptions, projective measurement, continuous measurement. But if I'm coarse graining my time and I'm just asking at the end, so what are the typical states on large timescales and large distances, it shouldn't matter whether I'm doing projective measurements or continuous measurements in this case. But it's easier if I want to go from the microscopic physics to the long wavelength physics by kind of elaborately forgetting details that don't matter, then it's easier to start with a continuous formulation right away.
Right.
So that's the idea.
I see. No, that is also very helpful, because we'll jump around a bit because this is quite detailed, and it would be nice to get to what the field theory description is. But here you've sort of laid out, I mean, the reason I'm going through this a little bit more slowly is you've just laid out the basic picture, right? As in the sort of prototype for whatever follows. And I think that it's quite instructive to see that. So great. Now you get to what are called these dark states, which is sort of terminology that again carries over into the field theory case. So could you explain what those are?
Yeah, so in principle, a dark state is coming is typically what we imagine a situation when we have an evolution coming from maybe Hamiltonian and environment. So we not have a purely unitary evolution, but we have some unitary plus dissipation or unitary plus projective evolution or so on. And so what we imagine now is that this evolution that we're looking, if we're looking at back at equation at equation 8, I think, then we see, because the Hamiltonian does not commute with the measurements, we will not end up in a dark state. So we will never have that this equation on the left, we have d of psi is 0. This will never happen.
I see.
And the
So
reason
is that the definition of a dark state? So
no, the definition of a dark state is when it would happen. Yeah. So when
yes,
we
yes.
have
So
kind of deep psi is 0, of course you can say then every 0 energy state would be kind of a dark state, but it applies more to this scenario where we have a competition between
yes,
unitary and dissipative terms. Then at some point, you imagine what you're having is you have a state where your time evolution really terminates, and you will approach the state. And this is a dark state. And this is just coming from the, I don't know, from the 60s or so, from quantum optics, where dark means you're shining in. Open system is kind of you're shining in light into your system, and you want to see how this light is reflected.
Yeah.
And the dark state is just, you don't see it because it doesn't reflect light. And this means it decouples from the light. And that means the system has kind of a stationary state, which you're not perturbing anymore by sending light into the system. So it's dark. It's a very simple thing. That's kind of where this comes
from. That's very fascinating. So it would, I see.
And
so there's some,
so this dark state, we would have it if we switch off the Hamiltonian, because then no matter with which state we start, we would end up in a state that is an eigenstate of all the measured operators. Yeah? So we measure fermions, but there are many of them. Yeah? So kind of if we're not starting in an eigenstate already, then we have many different eigenstates that are compatible with state. It's like a huge product of Born probabilities. And you say, if let's say I initialize my system in the ground state of a translational invariant Hamiltonian, and then I measure local particle numbers everywhere, I can get anything. I can get the nil state 1, 0, 1, 0. I can get a super phase separated state, just 1, 1, 1, 1, 1, 0, 0, 0. And I can get everything in between.
Yes.
And which state I get to does not depend, is not deterministically dependent on the initial state, because it's a measurement. So when I start with the same state and I do the same measurements, I have random outcomes, and I cannot predict these outcomes before. I can only tell you the probabilities, but I don't know. I cannot, there's no way I can tell the system, you need to measure 1 here.
I see. Yes.
And so you will get, if you repeat this measurement again, you will get with a very high probability a different state.
Yes.
And actually, if you are not starting
sorry, and all this while we've switched off the Hamiltonian,
this is all when we stop the Hamiltonian, but this is important because this was something one had to figure out. So there is a large configurational entropy.
Yes.
So if I measure 10 times an observable that has like binary outcome, +1, -1, or 0 and 1, I have 2 to the 10 different measurement outcomes.
Yes.
And since the state depends on the measurement outcomes, I do the same thing. I do measurements at the same locations at the same time, but I can get 2 to the 10 different states just for 10 measurements. That's not much. And now imagine I have 100 particles, I do 100 measurements. I have 2 to the 100 different measurement outcomes. This means I have 2 to the 100 different final states.
Yes.
And even though the competition between the Hamiltonian and the measurement guides you into a state that is similar, it's similar in the sense that it has the same type of correlations maybe, or the same type of entanglement. If I just look at local quantities of the state, I have 2 to the 100 different answers.
I see. So you're saying that it's not like, okay, so in the case we shut off H, and then we're asking for solutions of d psi equals 0. as in with whatever remains.
Yeah.
It's not
I
like
just
you're
let
really,
this.
yeah, you just have the stochastic process, but
Yeah,
it's
yeah.
not like it's landing you necessarily on a given readout, right? If we're just thinking about it as the end result as being a readout, it's not just giving you one, it's really
Yeah.
putting you into a configuration space, an ensemble of these kinds of readouts, which has a certain entropy associated to it. Isn't there some?
So each wave function will give you one readout at the end.
Yes,
So
yes,
if I initialize it, it gives me one readout, but if I repeat it, it will be a
yes.
different one. And if I'm
I see.
looking at the whole ensemble, right, if I want to know what is the ensemble of wave functions that I get, it's as mixed as possible because it's a
I see.
combination of all the possible measurement outcomes. And that is crucial because if I want to distinguish two quantum states, I need to do many measurements on the same state, right?
Yes,
So
yes,
if let's say I have two wave functions and I tell you, tell me the difference just between these two wave functions, it's almost not possible. Yeah, maybe there are some interference measurements, global ones that you can do, but just by, for instance, saying, okay, you can try to measure local correlations, but actually you can't, because once you measure something, you change the state, and
yes,
if and you don't know what the previous state was, and so it's very
yes,
hard to tell the difference between wave functions just by two measurements. So you need a large number of copies of wave function A, such that you can do many measurements and build up a correlation function on state A. And you have to kind of have many copies of wave function B to make many individual measurements, because correlation functions are built up by measuring eigenvalues repeatedly,
yes.
many.
I see.
And so if I have a different measurement outcome, I have a different state. It's
Okay,
not the
okay.
same state because it's not deterministic. And I would
Yes.
like to compare two states that have a different measurement outcome, but that had the same rate of measurements.
Mm-hmm. Yes. Yes.
Theoretically, we can do that because we can measure a wave function without killing it, right? So we can just pretend we have many copies because we have stored our state somewhere on our computer. But in an experiment, I cannot do that. So,
Right.
and
I
that is
see.
a big problem here.
So I mean, I should correct the statement that, well, I mean, it's essentially that the d psi equals 0 equation without the Hamiltonian, it has, yeah, it basically has this immense number of solutions.
Yeah,
As in, it's not at all unique what the solution to that equation is. And that
exactly.
you need to appreciate this fact when in reality you need to actually distinguish between between states that you get at the
Yeah,
end of
yeah,
this. Great. So now when you sort of turn the Hamiltonian back on,
yeah.
what's yeah, so what's the story there? So presumably you want to you okay,
So
so I suppose
one has to take a step back. So what we see is we do these measurements, we have the
yes.
Hamiltonian on, we get a certain type of wave function.
Okay.
Now we can look at this wave function. It's a very random wave function. It's not translational invariant or anything, because we had
Yeah.
all these measurements with different outcomes that are unpredictable. So if we look at correlation functions, they're not translational invariant. If we look at any quantities in these wave functions, very complicated. But what we can look at entanglement entropy.
Yes.
And entanglement entropy is a nice quantity. I can tell you, I want to tell you in a second why I like it so much in this context. But when we look at entanglement entropy, we see that the entanglement entropy is almost deterministic. So if I tell you I'm measuring this wave function with a rate gamma, and I have a Hamiltonian, which now the scale is 1, and I evolve it over time up to a certain point, and then I measure entanglement entropy, then entanglement entropy does almost not depend on the measurement outcomes.
Yes.
Essentially, the structure of the entanglement entropy does not depend on it. There's a little bit of wiggling, a little bit of noise on top, but whether I have an entanglement entropy that grows with the system size or whether I have an area law, this does not depend on the measurement outcomes. But if
Yes.
I'm trying to look at correlation functions, they depend strongly on the measurement outcomes. So if I measured 0 or 1, even if I do the measurements again, I emphasize this at the same position and at the same time, but I allow that I have these random outcomes, which I cannot predict before if I'm in a realistic scenario. And so the wave function looks very different, but it has the same type of long-range correlations built in or not. That's what the entanglement entropy tells me. But what I need to know for a measurement is how are these correlations encoded? So for instance, if I'm thinking about a one-dimensional kind of disordered Ising model, so where I have bond disorder, and if these bonds are strong enough, I will always have an equivalent to a ferromagnetic state. But depending on the signs of the bonds, sometimes the ferromagnet actually looks like an antiferromagnet, or it looks like a ferromagnet. And if I'm just summing over the average magnetization, I will get 0. But if I know what all the bonds are, I can sum over the flipped or non-flipped kind of magnetizations, and then I see it's equivalent to a ferromagnet. And here it's much more complicated. So what happens is entanglement entropy tells me I have quantum correlations that are long range, but maybe sometimes they are density. Maybe sometimes there is some density phase. Maybe sometimes they are current, or whatever. And if I'm just summing over all outcomes and say, what's the density correlations averaged over all outcomes, the result is actually garbage. Because there is nothing encoded in this. It's just kind of telling me this could be sometimes something that is non-trivial, but in another case, it's just the opposite. So at the end, I'm getting nothing.
I see.
And the only thing where I get something out of this is these kind of somehow basis independent measures of correlations, namely entanglement.
I see. Wow.
And this we want to explain here by saying, look, what happens if we're not looking at individual wave functions, but let's look at the ensemble average, where we say we build the ensemble of wave functions where we average over all measurement outcomes. Then this ensemble is described by equation 14.
Okay. Right.
And equation 14 has this structure that rho appears only in commutators with Hermitian operators.
Okay.
And now if I insert the identity, then that's the solution. Because as I insert the identity, all the commutators are 0. This means the identity is a solution of this thing. That means actually that the stationary solution for the ensemble, if I take the statistical ensemble of all the measured wave function, is the most boring state you can imagine. It's the identity.
Okay, I see. So that's the sense in which you said that there's the maximal possible configurational entropy in this.
Exactly.
Good. I see. So it's like that's like the high infinite temperature limit. Very cool.
So in a sense, it's a similar scenario as you say, take a disordered system. So take like a 1D disordered system, and now take where you have a Hamiltonian that has hopping and it has random on-site energies, and now average over all disorder realizations. That means the Hamiltonian averaged over all disorder realizations is translational invariant and boring. So you don't see any remnants of Anderson localization in this Hamiltonian because you did a stupid average. Each wave function is Anderson localized, but at a different position. If you average over all the possible randomness, then all these positions are flattened out, and the result is no signature of disorder. And the same happens here, where you say, now you have disorder in space and time, which are these measurement results. But if I'm too stupid, too naively averaging over this, I get a result that tells me, well, you just get nothing. You just get kind of the most boring state you can imagine.
Okay. So what should we be doing? I guess that's what the next section goes on.
So we had some reverse engineering by kind of looking, okay, what's special about the entanglement entropy? Special about the entanglement entropy is that it is a quantity that is already nonlinear in the state itself. So I need to compute. I need to look at a wave function, then I need to do some nonlinear modification of the wave function. I get a number, and then I can average this number, and suddenly I see great stuff. This is, of course, people coming again from this disorder. They say, well, I mean, that's kind of not surprising, because you have to do the right average. So you have, for instance, to do this replica averaging that everyone in disordered systems is familiar with. The point is just you have to extract the useful quantities first and then do the averaging.
Yes.
The entanglement entropy is one thing, but what we discovered, what's another interesting quantity, is a covariance matrix that we're averaging. So some nonlinear averaging. I don't know if it's in this paper. So that there, yeah, so equation 15.
Yes.
So we just take 2 points in space. Now they're labeled with 1 and 2. And if we're looking at the first expectation value, it's the density correlation that you would normally look at, and then you average it over all measurement results. But because this is linear in the state, you can just take the state that is the ensemble of wave functions and compute this. No interesting behavior, yeah, no signature of this. But if you look at the second part, what that you subtract, usually this is the part you just subtract for normalization or something, so you're not really interested in this part. But actually this part is non-linear in the state, because you take 2 expectation values, so it depends on row and row, and then you average over it. And so what you're not kicking out are statistical correlations between these 2 rows now. So these are kept. And now suddenly this is an interesting quantity, this correlation function.
Very interesting.
And we were guided by this and said, can we write this nonlinear function as a linear function of a state? Yeah, well, you can if you
Yes. So if you introduce replicas, basically.
Exactly. So you introduce replicas. And now say instead of introducing a single wave function or a single state, I introduce 2 copies of the state. Both copies have the same measurement outcome. But then when I have these copies, I average over all the measurement outcomes. And now I have these correlations between these 2 guys. They are built in, these statistical correlations.
Fascinating. And of course, I mean, it's completely consistent with what you explained with the entanglement entropy being a useful measure in this context, because that is indeed like the way you compute it in practice in a lot of cases is through the replica trick, which basically contends, it just linearizes the calculation in a sense, right? In some, there's some density matrix with respect to which there's some limiting way of looking at a linear operation on it that reproduces this nonlinear object that is the entanglement entropy.
Exactly.
And what you're saying here as well, I mean, you can do other things in that context too, which would be nonlinear in the state, and you get all these interesting results. Very fascinating. So now I suppose what we should try and look at are some characteristic behaviors, and then maybe flash the field theory stuff, although going there is not strictly necessary. But just to get a sense for what happens in this Dirac fermion story, just for a sense for what are the different phases that you see, right? So I guess we should briefly go over the setup, right? So you have a well, sort of 1 + 1 dimensional setup where you have Dirac fermions, and the measurement, or the things you're measuring are densities and currents, basically. And here you say that, well, the dark states, right, are these products, and of course there's quite many of them, given by the fact that there's quite many sites on the lattice in principle. And the stochastic Hamiltonian, this non-Hermitian Hamiltonian, involves now the following sum, in addition to the regular Hamiltonian, over these 2 measurement operators in this piece.
So the key thing we wanted again to have a field theory for description. So we have now the time continuum, but we want to go to the spatial continuum as well. And so of free fermions, the natural choice maybe is to look at Dirac fermions. And then look at measurements. And what is important about the measurements? So an important thing is the measurements need to be non-commuting with the Hamiltonian. That's important.
Yes.
Because
Yes,
if they
yes.
are commuting, then not much will happen. We will go into the measurement in some measurement
So
eigenstate,
just
but
go up
because the
here.
Hamiltonian does not commute with the operators, we will just stay there. And so we can forget essentially the Hamiltonian. So only the
Right.
Hamiltonian only matters if it does not commute with the two. And so in equation 17, this kind of backscattering type density O2 would be sufficient. This does not commute with the Hamiltonian, while O1 commutes with the Hamiltonian. That's kind of a forward scattering type density in this condensed matter language. But we included this type because if we just take the densities of fermions kind of in the lattice language and bosonize this straightforwardly without thinking about it too much, then we also have this. So, or in other words, like a typical local density of fermions is composed of these two types of density.
Yes.
And so, and
And
then we more
this
or
is in
less
the bosonic language.
straightforwardly, right. So this is kind of the forward scattering type density O1, and O2 is a backscattering type operator or vertex operator. And so we're bosonizing them straightforwardly. So, I mean, this is like, you could say, well, how much is bosonization defined in this setting because we're not in a low energy manifold or whatever, but we're saying, okay, let's do it and see what happens. But you could also argue we motivate this model by Dirac fermions, and then we come up with a bosonic model, which essentially has the same properties again. So this is a Latin with Hamiltonian. It's a quadratic model, like we have a quadratic model for the fermions. It is translational invariant and has a kind of a well-defined kind of ground state, like the free fermions. And now we measure some operators where one part commutes and another part does not commute. So this is so
Right.
if you don't believe all of this analogy or this story, then you can just start here and say that's what we're doing right now.
Sure. Yeah. Yeah.
I think
Perfect.
it's
Yeah.
justified a posteriori by the results, but I mean, this is more or less showing the similarities or the analogies between these models.
Great.
And here again, like these measurement operators, they have an eigenstate where this phase field or this density field phi is well defined. So if I'm in an eigenstate of this operator phi, then the measurements don't change the state, but the Hamiltonian has this dx of theta, which does not commute with phi, and so it pushes the system out of the state.
Right.
And so the entanglement transition or the measurement induced transition is then here really the same as a pinning transition by measurement. So the measurements try to pin the particles or try to pin the field phi to a well-defined value, while the Hamiltonian tries to delocalize the particles or tries to kind of make this field phi non-well-defined. So that's the scenario.
So I mean, this will probably be the thumbnail, but do you know about these fictional monsters in the famous British children's show Doctor Who called the Weeping Angels?
I know Doctor Who a little bit, but not enough to kind of to kind of elaborate on that. So, but
Well, I mean, these are I think this is one of the best sci-fi uses of the quantum Zeno effect, where you have these monsters that, so long as they're measured, which literally means you look at them, they look like statues of weeping angels. But if you avert your eyes, they start to move. And if they get a hold of you, something very bad happens. So it's exactly in the sense that you have competition between the measurement and the evolution, right? So the Hamiltonian is kind of the weeping angels coming to get you, but then the measurement is basically whether you look at them. And of course, you can't just keep looking at them. So there's some weak measurement scheme that people come up with, the doctor and his companions, to try to escape these things whilst making sure that you can pin them long enough for somebody else to do something else and you gotta run away. So it's very fascinating. And the seasons where those were featured were one of the best of the show. So Anyway, that gives me a nice
No,
thumbnail for this
it kind
video.
of it looks it kind of really matches very well this description where you say you have some
Exactly.
kind of quantum xenotype evolution from the measurement, and then the Hamiltonian tries to mix up this state, but it might be not strong enough. You know, so
Right. So I guess we can jump also to the net effect of the
yeah,
analysis here. And what happens is that there's a weak monitoring limit where you have the following behavior of, well, I guess we should jump to what these correlators are, but they're basically formed in exactly the way you mentioned before. But what we do
yeah,
now is basically sum up the two kinds of
yeah,
operators and then
yeah,
compute their basically stochastically averaged
yeah.
correlation function.
So
And
this
here,
is the analogy of a density correlation function that we're looking at, but again in this framework where we are taking first the density correlation function, and then the density on one place, the average times the density at a different place, and then take the statistical average. So these are kind of the non-trivial ones. And
right.
that's what we're looking at now, either in k-space or in real space. And this is what we get. So in the weak measurement phase, where we see this logarithmic growth of the entanglement in individual wave functions, we see that in this replica theory, we now have correlation functions that decay algebraically like 1/distance square,
Yes.
which kind of, yeah, shows us or kind of, how I say, confirms this scale invariant behavior more or less here.
Right. And so then, yeah, indeed, because you have this algebraic decay, it's much like having some scale invariance manifest, and then you expect that the entanglement entropy is this logarithm
Right.
of
Yeah.
so basically, of L, where L is the region you've kind of traced out.
Yeah.
Next, let's go to the strong monitoring limit, right? And this is kind of the ideal scenario when you have to escape from the weeping angels, where
Yeah.
you have this power law decay. And now there's a correlation length again set by gamma,
Yeah.
which
Yeah.
right. And you should walk us through what this V means here and the different
Yeah, so
options you
this
have.
V is this V is more or less the scale of the Hamiltonian.
Right.
So if you think about Dirac fermions, it would be your velocity. In this Latinger liquid Hamiltonian, it's also the prefactor of the Hamiltonian. And so in principle, gamma over V is more or less the competition between the rate with which you're moving versus the rate with which you're measuring. So in this,
Yes.
and so once this rate exceeds a critical value, which means you measure more often, you're in this quantum Zeno regime, and then your correlation functions are exponentially decaying with some correlation length that we have here, more or less. So
Yes.
in this expression.
Yeah. So of course, if you take V to zero, this will just
Yeah.
go to zero, and then yeah, that's kind of the totally projective kind of
Yeah.
situation.
So that's really the competition between two rates, the rate of particle spreading versus the
Yeah.
rate of measurement. And then again, measurement means localizing a particle. So, but you do
Yes.
this dynamically. So it's not Anderson localization. For Anderson localization, you would have that everywhere you have exponentially decaying correlations and you wouldn't find a logarithmic growth. But here, the disorder is in time and space from the measurement,
Yes.
and it's non-unitary. It's kind of
Right.
so this is different from Anderson localization.
Fascinating. I mean, in light of time, we should maybe wrap up here because I feel like we've sort of hit the sort of basic
Sure,
uh
sure.
key points behind the rest of the story. I mean, we can sort of jump around a little bit and sort of flash the
Yeah,
results you have in this field theory case. You developed quite nicely a replica formalism
yeah,
that tells you what's going on, and
yeah.
quite
So maybe
interestingly, you
here.
have this, yeah, you find this behavior involving a non-unitary extension of the Sine-Gordon model.
Yeah, yeah.
And you
So
have this kind of evolution of a density matrix that almost looks like what you expect with a commutator, except the non-unitarity means the non-Hermitian nature of this Hamiltonian means H dagger is not H, and so you can't just write this as a
Exactly.
commutator. But that's yeah. So just maybe you could tell us briefly, like how do you land on something like this?
So what happens now? We said we introduced these two replicas
Yes.
because if we take a single one, then we see the system just goes to this totally mixed state.
Yes.
And this totally mixed state is either you can say, well, it has no information, it has a lot of this configurational entropy, or you associate this with some infinite temperature state, right? So if you,
Yes.
no matter which Hamiltonian you have, if you send a temperature to infinity, you will just have the identity. And so this is kind of an infinite temperature state. Now we introduce these two replicas. And what happens, because we now have statistical correlations between the two replicas, we don't have the same evolution as just a single replica. If we're looking at this product, this will still have, if we're computing just plain observables in one of the replicas, let's say density correlations in the first replica or in the second one, then that's the same as we would not have introduced the replicas. So they both lead up to infinite temperature. We can just trace out one replica and then compute the correlation functions. But what's interesting is the correlations between the two. And these are best expressed by doing a basis transformation and not talking about a replica number 1 and a
Yes.
replica number 2, but kind of an average coordinate of the two replicas and the relative coordinate. And the
Yes.
relative coordinate is really something like the quantum fluctuations between the two replicas, while the absolute replica or the absolute mode tells me, okay, so what is this absolute state going for? And so we can easily imagine that all this configurational entropy is kind of taken over by this absolute coordinate, which tells us where does this on average move. On average, the evolution again goes to this maximally mixed state because I have this entropy. But if I'm asking about the quantum correlations, now they are kind of actually going in the opposite direction. They are described by this non-Hermitian Hamiltonian, and this non-Hermitian Hamiltonian acts like a cooling, right? So if I'm looking at this, it has now eigenvalues that are complex, and so I'm evolving towards the state which has the eigenvalue with the lowest or smallest imaginary part, or depending on how you read it, the largest one, depending on if you're looking at H or H dagger. And so that's where we end up. And so no matter what we start with, we actually go to a pure state and not to a mixed state. So this always purifies the system, and this replica, this relative replica coordinate, or this replica fluctuations, they are going towards now again a dark state because it's a pure state where this Hamiltonian acting on the state gives us 0.
Yes.
So this is kind of the state where we're going for. And this Hamiltonian has this funny shape where we have a sine-Gordon model, but now with complex coefficients.
Yes.
And this is important, that both of these coefficients, like the one in front of the scale invariant part or the dx phi square part is complex, and the one in front of the cosine part is complex. If we're ignoring the cosine and we're looking at the first part, then this actually cools any initial state close to a ground state of a latential liquid, if I'm looking at this. Yeah, so
I see.
what happens is I'm just cooling down towards a scale invariant state, which is close to a ground state. It's not an exact ground state, but it has the same features like a logarithmically growing entanglement entropy and scale invariant correlation functions as a latential liquid in the ground state. The second part cools me towards a totally localized kind of configuration of this phi. And so we really have the type of competition that we expect from a sine-Gordon model in the ground state, but now we're having it dynamically in a dark state. And one can imagine, depending on which state is or which term is stronger, if lambda is super strong, then we will see that this localizes. If kind of the gamma, if kind of the kinetic energy term is strong, then this cosine term will renormalize to 0 and will be irrelevant. And so these are kind of the two phases. And yeah, so we are more or less then putting this in a path integral framework and analyzing this. and a kind of
Yes.
complex sine-Gordon models have been looked at. Yeah, that's exactly it. But now eta is kind of a complex variable.
Right.
And k is too. Or wait a second. No, I think eta is real, but k is complex.
Yeah, no, it seems eta is complex, at least
Both of them
here.
are complex.
Yeah, so they're both
That's what I
complex, and but yeah, here are your RG flow equations, one
yes.
for lambda, and the other for k.
Yeah.
Right, so
And
then
actually, it's important here. This model has been looked at if in the case where k and eta are both real, but lambda has this form that it's purely imaginary. And then actually what people find there is that you have a reverse scenario that lambda can never be relevant. So initially lambda
oh,
starts to grow, but then it always flows back to zero just because it has a sign flip compared to the normal. So if you look at the normal sine-Gordon model, you would erase the I in front of the lambda
yes,
and would make k and eta real. And then what
yes,
you have the scenario that lambda can grow and k can grow, and depending on which one grows faster, the other one becomes irrelevant.
yes,
But if you have this term like that and make k and eta real,
real.
then this means that lambda is growing, I think, but k is shrinking always. So and
Oh,
then you will just arrive at the point where if k is small enough, lambda is also kind of shrinking again and becomes irrelevant. And so you're always going to the free theory, like the
uh-huh.
scaling variant theory. And here you have both of them complex. And if you look at the RG flow of these, what you
Yes,
see is that you get some kind of non-Hermitian wiggling where this complex behavior comes in. So these are the black lines on the right. But you
yes,
can always find a corresponding Hermitian flow where
aha,
if you look at sufficiently large distances, wavelength, you actually recover the thermal or the ground state flow equation. Yeah? So you have
I see.
some, it might take long, the closer you're to the critical point, might take long distances, but on the largest distances, what you're getting back is the flow from the ground state sine-Gordon model.
Very
And on
interesting.
intermediate scales, you see these non-Hermitian effects giving you
Yes.
kind of these oscillations instead of a well-defined graph.
Yes, and so here you're able to plot these because you're looking at the magnitudes only of the complex,
Right.
of the complex couplings. No, but that's
Yeah,
very fascinating. Yeah, I mean, these are things that people in my field have started to want to understand better as well. And it's a longer
yeah,
story to go into exactly why, but it is very instructive to know that there's this concrete physics behind what's happening here. And yes, it's much appreciated. And so in the rest of the paper, you do go on to also compute the entanglement entropy, which indeed,
right.
well, okay, through you need the n replicas now, and you compute a Renyi
Yeah,
entropy and then the entanglement entropy, but you do find in this section that there's the kind of transition that you mentioned quite
yeah,
generically in terms of correlation functions, also manifesting at the level of entanglement.
yeah.
So that I think is also important to
Maybe
highlight.
the
Yeah. So
maybe
I mean here
the
we can,
important, huh?
yeah. So we already see like I mean
Yeah.
the end results here. But anyway, yeah. Go on.
I think the key part that also surprised us is that in the entanglement entropy, you said it is typically also computed even for ground states. You go to this replica construction, right? And the funny thing is that this replica zero mode, actually this absolute mode, this always drops out in the entanglement entropy, yeah, because it's the k equals zero. It comes with this k prefactor. It does not contribute to the entanglement entropy, and that's what we see here. Is that this absolute, this mode that kind of accumulates all this configurational entropy simply does not show up in the entanglement. This is totally, the entanglement does not care about the measurement outcomes. It cares about the correlations that are imprinted in the system. And these
Yes.
correlations, as we said, these are always the same. They are just in a different representation each time, but the entanglement does not care about this representation, which is kind of manifest by saying this absolute or this center of mass mode, which has this information, is not relevant for the entanglement entropy at all.
Very interesting. Right. So in some sense, the entanglement only cares about the shape of whatever's going on in this crazy ensemble, not really its size or whatever. That is so fascinating.
So in principle, I can say I have 4 different Bell states. If I look at 2 spins, I have 4 different Bell states. They all have the same entanglement, but they all have different correlation functions if I'm computing them. But correlation functions, I don't care. I just want to know, are there the correlations between the 2 spins or not? And this answer is given by the entanglement. If I want to know which are the correlations, I have to look at the correlation functions. But this answer, I don't care. I don't care which Bell state I get. I just want to know, is this a Bell state or not? That's more or less also the question here. Is this an entangled state or not? Do we have quantum correlations or not? I don't care how are they encoded in the state.
Very interesting. No, that is so fascinating. What I like is that the underlying emphasis on what the physics of the things we normally do actually even is, right? I mean, here you have a sort of monitored continuous measurement story, but ultimately, like, what are we doing in some kind of, say, Bell's inequality type experiment? Well, we're going into this ensemble, we're pulling out specific records, and we're sort of comparing them and saying, oh, look, here are the correlations we're building and associating to the entanglement entropy, right? And then you sort of, on average, that's what you do. You sort of accumulate these correlations and see that there's a certain behavior I would think of as being my maximally entangled behavior, and here you're sort of like cutting straight to that question from this replica picture and looking at the entanglement entropy and so forth. But indeed, it's like you can only talk about, I mean, how do you talk about these? I mean, the use of the replica method, you know, when you talk about disorder or when you're using it in this context, is always to make sense of these kind of counterfactual statistics where you say, well, okay, I ran the system. If I'm just sitting evolving with the system and then I'm taking readouts, then I'm stuck in whatever silly dark state that I'm stuck in, right? Like at the end of the day, it is just this jumble. But what I really need to be doing is something quite different. I need to be drawing statistics by making these reruns. And I need to be able to talk about correlations happening, you know, in different places of this configuration space. And the only way to do this, or an easy way to do this, is to just go to the replicas system, right? Where you just have, you know, maybe you copy this, do it twice, but I mean, it's kind of a cartoon way of thinking about it, but indeed, that's always the use of it, even when you just have disorder, right? Like what you're trying to say is look at different noise realizations, but instead of, you know, like following one given noise trajectory, you need to sort of like have access to copies of the system.
So because, I mean, like for disorder, each individual state is random. So what kind of statistics, what averages are you talking about? You want to talk about average quantities that I see in any of these states, but if I'm just naively averaging, I don't see them because they are vanishing. So I need to find a different way. And what you mentioned is, of course, then something, well, replica works in theory, but what do I do in an experiment? So for disordered systems, I can still say what I can do is I take my disordered system, but disorder is quenched. It doesn't change over time. So I take the same sample and measure again and again and again. And so I build up these expectation values and then I can average. But for the measurement, this is even more complicated because this is also varying in time. And so I cannot just present the same state and measure again. There's, of course, the simple solution is called post-selection. Say I measure 100 times. I know all these outcomes, and now I measure another wave function again 100 times, and if I don't get the same outcome, I just throw this away because it's not the same state. But as we already said, 2 to the 100, that's a lot. So you
Yes.
have many wave functions that you throw into garbage. So and that is not feasible anymore. So it
Yes.
has been done just as a proof of principle for small systems, but actually there comes a connection to these systems of these systems to error correction, where you say,
Yes.
well, what I can do is maybe I can react on a measurement outcome. I record the measurement outcomes. I know them. That's information that I know. If I just focus on the final wave function that I get and I neglect all the measurement outcomes, then I'm throwing away a lot of information. But what I actually should look at is kind of the whole record of measurement outcomes plus the final wave function. And for
Yes.
instance, what you can do for some states is to say, well, if I know the measurement outcomes, then I can apply another set of unitary gates, which I determine based on the measurement outcome in order to correct the state such that is the same as one where would have measured something different.
I see.
This works in some cases. For the fermions, it doesn't work.
I see.
Just to make this clear, it works for very specific, for Clifford circuits, it works, for instance, where you can simulate the whole evolution in parallel. But in general, kind of that's now a big question in this field, where say, I mean, people have many reasons looking at this measurement-induced transitions, but one is, how do I see this in an experiment for a generic kind of type of evolution? We also have some recipe what to do, but this is kind of still under review, and there's also discussions about whether how general it actually is. So just I would say let's see.
Okay.
But this is kind of ongoing research now, how to actually see this, because it's nice to say, well, it has great entanglement, but if I can never measure it, I mean, it's as useless as if there was no transition. It would be just kind of a playground for theorists, essentially.
Yeah. Well, no. That is indeed the question to then go back and answer the earlier conundrum about the cat and whether
Yeah.
the quantum mechanics leaks beyond the. Yeah, so you probably couldn't talk about
Yeah.
that unless you could identify which phase in the analog of this you're in. I mean, of course,
Yeah.
the environment probably doesn't just have a couple of these, it probably has a lot of these measurement operators that it has
Yeah.
access to. But ultimately, it is still a very similar question. No, so that's quite fascinating. I mean, or is that do you agree with that statement that the difference when you have an environment is that, well, it has access to just many other kinds of
Yeah.
uh
So
terms and
I mean, an environment typically comes with a Hamiltonian that couples to the
okay,
system. And so
right,
what you're doing is actually you are entangling your system with an environment. And whenever you try to project on your system, this must fail because you're actually entangled. And
right.
so the statistical mixture that you get as a result is a real thing in that sense, because is really describing the mixed state of the system because it's entangled with an environment.
Right.
Here, here actually what happens is that each individual realization is a pure state, which you don't have when you couple a system to an environment which is entangled with the state.
Yes.
Here you always
Yes.
have a pure state, but you have a random pure state. And the funny thing is, there's really no way in experiment, if I give you an ensemble of pure states and just one ensemble where, say, that's the wave function of the system, it's a mixed state, there's no way that you can distinguish the two. So if I'm sending you random pure state wave functions that build up this ensemble, or if I'm giving you the ensemble, there's no way in an experiment that
Yes.
you can distinguish between the two. That's the funny thing. So one is an ensemble of pure state wave functions where the only thing that's missing is classical information to make sense of them and to distinguish them. The other one is really the ensemble where you have
Yes.
where
A
there is
truly
no
mixed
pure state
state.
wave function.
Yes.
The system is in a statistical mixture, but without this additional information, you cannot distinguish the two.
Right. I see. Well, yeah, I mean, but I mean, isn't there a way to sort of segue between them where you just say, I can just add a number of other operators. So from the perspective of the system that I'm initially evolving, I can just keep adding the rest of the operators that form yet another Hamiltonian.
Yeah,
And then
so I mean, then if I'm completing this with the whole system where I have a
yes,
pure state versus then that's true again. But then this kind of in the same way, that's the same information where I say I need information to this measurement outcomes, or I need information onto the environment that tells me
exactly.
what actually happened in the environment, because there's this information that I throw away, right? So I'm in both cases, I throw away information, and without having that information, I just cannot kind of access the full knowledge about the system that I could have. So that is I can't tell the difference.
I see. Right. No, that's very interesting. Indeed, I guess the important distinction is that you just have a density matrix to begin with. There's no pure
Yeah,
state
yeah,
story. Here you do have a pure state,
yes.
but you do statistics over it in principle. No, this is very educational, Michael, and it will take me a little bit longer to truly absorb all of this, but I think I have a much better understanding now than I did before, and I think that there are many. I mean, there are many interesting ways to go if we start to
Yeah,
ask
no.
about, yeah,
This, we, we we just had a conference about this topic here in Cologne,
yes,
and at the end there were just more questions than answers, I would say, which is great. So some guy said, yeah, we now have more work to do, so that's good. So we
yes.
have a reason to be paid.
Yeah. Perfect.
Mm,
Oh, thank you
yeah.
so much, Michael. So if you've made it this far, please like, comment, share, and subscribe. This is Theoretically Podcasting, and I will return next week.